Hello again. This is Math 1120 coming to you from the College of DuPage, and the title of this lecture is More Waves, Boundary Behavior, Snell's Law, and such. And I encourage you, as always, to be an active learner as you watch this video. Sound waves and electromagnetic waves have similarities and differences. We'll note the differences, but we're going to emphasize the similarities. And key similarities are found in the boundary behaviors, and this will include Snell's law. So, by way of introduction then, Faraday's law tells us that a time-varying magnetic field acts as a source of an induced electric field in terms of inductance and transformers. And in 1865, the Scottish mathematician and physician James Clerk Maxwell proposed a time-varying electric field could play the same role as a current as an additional source of a magnetic field. This two-way interaction between magnetism and electricity forms the basis for the field of electricity and magnetism, and is summarized elegantly in a set of four equations now called Maxwell's equations. Now these equations are really very complicated mathematically, involving all kinds of third-term calculus kind of things, so we're only going to explore the primary prediction of these equations, but we will talk about electromagnetic waves and, through analogy, sound waves. So here are some electricity and magnetism basics, and again we're going to be emphasizing the similarities. The wave is transverse, just like the sound wave could be represented by a transverse pressure or power curve. Both E and M, these are vectors, the electric field and the magnetic field, are perpendicular to the direction of propagation. And by the way, that's the same thing that's true with the longitudinal sound wave. The transverse wave is perpendicular to that. And so they're perpendicular one with another and to the wave itself. Now, so we'll look at a picture of this in a bit. In the case of electricity and magnetism, there is a definite ratio between their magnitudes of these, and that ratio is called C. And it turns out C is the speed of light in a vacuum. And the speed of light in a vacuum is a definite and unchanging speed called C. We'll talk about its speed in a minute, but that is an amazing thing that is unchanging. Now, unlike mechanical waves, and this is a place where they are different, we need to have, for a mechanical wave, a sound wave, we can't transmit in a vacuum. We need some oscillating particles of a medium, such as water or air, to be transmitted. Electromagnetic waves require no such medium. In an electromagnetic wave, it is the electric and magnetic fields that are waving. We have magnitude and direction. Here we talked about the magnitude, which is the speed of light. The direction is determined by a thing called the right-hand rule, which is described here. You point the thumb of your right hand in the wave's direction of propagation. So the wave's going to be propagating this way along the y-axis, and your fingers in the direction of the E field. So we point here with our thumb and there with our fingers. But then what we're going to do is, holding our hands in this position, we rotate our fingers 90 degrees. They only move one way. It goes this way. And your fingers point in the direction of the B field. So you can see that the B field and the E field are perpendicular one with another. And this is the direction of propagation with the wave, which in a vacuum travels at the speed of light. Electromagnetic waves cover an extremely broad spectrum of wavelengths and frequencies, and sound covers many wavelengths and frequencies, but not as wide as this is. Radio and TV transmission, visible light, infrared, and ultraviolet radiation, X-rays, and gamma rays are all parts of this spectrum. And the spin of this spectrum is shown in the figure below. So you see we go from 10 to the minus 13 in terms of wavelength, all the way up to 10 to the 22, which are gamma rays coming from the sun. And there's only a small part of this spectrum that we really can see, that's the visible light. Notice that this is the same as with sound. There's only part of the spectrum that we can hear. We can hear from 20 hertz to 20,000 hertz. But we talk about megahertz in terms of ultrasound. So you see light has similarities, but a much broader focus. And the visible light that you see comes in colors, and it ranges from red all the way up to violet. And so that's the visible light spectrum. So as it says, we can only detect a very small segment of this spectrum directly through our sense of light. Within this visual detectable range, we perceive wavelengths or frequencies in terms of color. The long wavelength, red, to the short wavelength, violet. And some animals, including bees and birds, can see into the ultraviolet. Pit vipers use their pit organs to see infrared radiation. Some of your remote controls also broadcast in the infrared area. You cannot see your signals going to your television, for example. Okay, so as we said then, the wave will move in this direction, but the electronic field is this direction, and the magnetic field is this direction. And so it's really analogous to the sinusoidal transverse mechanical waves in a stretched string, or what we showed with the longitudinal sound waves. In this, we talked about those being perpendicular, and they share the primary wave that we have going along this way. And the property that in any instance the field is uniform and they're perpendicular to each other, and that's called a plane wave. So this wave is going in a plane. The red wave is moving in a plane. The directions of those are perpendicular to directions of propagation, just like the longitudinal molecules vibrating is perpendicular to the pressure wave in a sound wave. And look, the equation governing this looks exactly like the wave equation we had with that. Now, with sound waves. So we have the amplitude, we have a period, or could be a frequency because they're inversely related. We also have the wavelength shown this way. So it's the same equation, it's a lot of the same physics. In particular, we're going to be concerning about boundary behavior. So here is, we're going from air over here into another medium, which could be glass. I guess we're talking about this being inside of a glass. So what we have is, we have waves that are being incident coming from this direction and hitting the surface. And two things happen. One thing is that the waves are in part reflected, and part of them go in. So some are bouncing off and some are going through in general. As we're going to see, that depends on the angle. The ones that bounce off are called reflected waves. The one that goes through, and you see that they're bent a little bit, we'll talk about that, are called refracted waves. And often, rather than look at a whole bunch of these waves, we'll just look at a couple to understand them. And so here what we see is this wave comes in at an angle that we're going to call theta sub A. Now, the angles are always measured relative to the normal or perpendicular to the surface. That's important for you to understand. So this one comes in, and that is theta sub A, and this is theta sub R. That is the reflected wave. But inside, what you see is a refracted wave, and notice that the angle drawn to the normal is different. In this case, theta sub B, the angle of the refracted wave to the normal, is smaller than this. So that's the phenomenon we're going to be studying at the boundary, and it shares properties with sound waves in much the same way. So we talked about incident rays, we talked about reflected waves, we talked about refracted waves, so that's all good. Now, if the interface happens to be rough, both the refracted and the reflected waves are scattered in many directions. So here is a rough boundary, and you see that those things will be bouncing all over the place. Both the reflected waves and the refracted waves would be similarly in many different directions. Various directions, and there's no single angle of refraction or refraction. We will devote most of our attention, however, in this chapter and also when we talk about sound, to smooth interfaces like the one up here, where there is none of that scattering, and the reflected wave travels at a definite angle. And this is called specular reflection, and this is called diffuse reflection. And so it's illustrated here, and as a physical analogy, when your bathroom mirror fogs up from the shower, the otherwise specular reflection in the mirror becomes diffuse. You look different as you look in the mirror through a fogged up mirror. A critical parameter that we have is called the index of refraction of an optical material, and that's also called the refractive index. It is usually denoted by N, and it plays a central role in geometric optics. And this is the definition of the index of refraction. The index of refraction of an optical material, denoted by N, is the ratio of the speed of light in a vacuum, which is denoted by C, to the speed of light in the material, and that's denoted by V. And here's the relationship. The index of refraction is equal to C divided by V. So a material, like the glass, will have an index of refraction. Light always travels more slowly in a material than in a vacuum. So that means that this is always going to be bigger than or equal to 1. In a vacuum, N is equal to 1 by definition. Now we're going to talk a lot more about this in the next video. But for now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other. God bless you all.